Screenshotter is a novel web app to quickly take notes and screenshots. To make screenshots, simply enter the URL of a website and the app will store a screenshot of it. The site is currently in beta, so only CSCG.de screenshots are allowed. This is a web hacking CTF challenge that I created for the Cybersecurity Challenge Germany. And for all those people who scoff at CTF challenges for being unrealistic, well, this is a completely realistic challenge. I found this vulnerability in a web app at work, which felt like a CTF challenge, so I got inspired to create a challenge with the same vulnerability. Of course, I adapted it for the CTF, but believe me, the steps for discovery and exploitation are very close to what I found in real life. So if you want to try it yourself, you can find the files on GitHub. I think this challenge can be really good exercise for doing real-world security audits of web apps. So why not give it a try and practice with it? When you look at the provided files, you can see it's based on Docker Compose. So if you have that installed, you can just type Docker Compose up and wait for the containers to build. And then it should be available on localhost port 5000. And yes, all of these files are part of the challenge. So you can read any code and really dig deep into the app to find the vulnerabilities. Of course, the Do Not Access folder contains the solution, so that is not part of the challenge. So now you have a few more seconds to pause the video, otherwise I will go ahead and tell you how to approach and solve this. Like with every challenge, the first step should be to get an overview of the functionality. Apparently you can log in or register, and this is a demo version which can only create screenshots of HTTP CSCG.de. There's also this activity tab showing you what's going on the app. And this is here to show you that there is a user Flagger which added a note and requested a screenshot via a worker service Chrome. And we see the screenshot also got successfully processed. The space64 value is obviously interesting, and this can be decoded to an IP address. Sometimes space64 values are stripped of the padding and then it doesn't decode nicely, so adding some equal signs here at the end makes the output correct. So no clue yet what this is for, but we obviously remember it. Now let's try to register and log in with the user. Here simply a test user, and now we can add a node. But the special feature is obviously screenshots. So let's try to add one by using the test URL, http://cscg.de. It's processing now, and when we wait a moment, we should get a screenshot of the website. Awesome. If we now look at the activity log, we can see that now we also appear here. Test user added a note and test user requested a screenshot. Cool. Pretty basic web app, not much functionality, but where is the flag? Well, we will see that soon. Let's head into the source code of the app. The Docker Compose file is always great to start with because it describes the higher level architecture or setup of this whole web application. And here we have three services. And we have a Chrome service, a screenshot service, and an admin service. Each of these services are built from Docker files contained in the respective folders. Screenshotter appears to be the main app. It's the one exposing the port 5000. The other services have no exposed ports. Depends on is a field that ensures that Docker Compose first sets up Chrome service, then the web app, and then the admin. So let's look at the services in this order. First, the Chrome service. The Chrome service is a simple Docker file. It basically only installs Chrome browser stable version and then starts Chrome in headless mode, so no actual browser window is opened. Also, you can see here that it enables the remote debugging port of Chrome 9222. But this port is not actually exposed, so we cannot connect to it. Okay, so this simply started Chrome in headless mode with remote debugging enabled. Now let's check out the main app. It's written in Python and more specifically the Flask framework. Before running the Flask server, it executes init.py. And here it seems to just initialize the SQLite database. It creates a database with commands from schema.sql. Checking that, we can see that we have a user table, a nodes table, and a logs table. And after setting up the SQLite database, it will also create a random secret. No clue yet what this is used for. Next, we have the main app. And right at the top, we see that it tries to find the IP address of the Chrome service. If we cannot get the IP dynamically, it will fall back to localhost. This IP will then be used in the screenshot function to connect to the Chrome debug port 9222. And in this other place, it is base64 encoded and added to the public log. So the activity log with the text username requests a screenshot via worker Chrome and the IP address. So cool, this means with this output we can get the IP address of the internal Chrome service. Now, just to give a bit of context, this IP exposure was not part of the real app this was inspired from. I knew from my experience with Docker that there are default IP ranges for Docker containers, usually starting with 172. So I didn't need an IP disclosure to know what Docker service internal IP could be, but I thought I could make the challenge a bit easier by adding this basic IP exposure to make it a bit less guessy. Also because I was not sure how the challenge was going to be hosted. I wanted to make sure that there is an easy way to find the internal IP of the Chrome worker in case it would not be the default Docker IP range. And it turns out on my Windows PC here, the IP is not the expected 172 IP. So I guess it was good that I added this. If this were not here, you would have to take educated guesses or scan the IPs if possible. Anyway, just after we get the Chrome IP, we also get the secret, and this secret is used in an HMAC function to create a signature of some data. And the signature function is called inBeforeRequest, which acts as a session middleware. It checks if we have a valid session in the cookie, so if we are logged in or not. Feel free to read this code more closely to better understand it, but it should all be safe. I just implemented some basic user authentication that is good enough for this challenge. So spoiler alert, this should not be important. But how do we approach this now? It's not a huge web app, but it's also not really short. Still quite a bit of code. Actually, when hunting for bugs in web applications, I like to go for the unique, interesting functionality. You know, every web app has to implement user authentication and stuff like creating nodes. That's all boring. But this app is interesting because it can create screenshots. And I like to go after these kind of weird features because this is where often the really fun vulnerabilities hide. So let's check out the API call that creates a node. We can easily find that by looking at burp or the browser dev tools when we submit the cscg.de URL to request a screenshot. So we simply call add node and the body contains the URL. Okay, so here's the route handler for add node in Python. Here we get the request body, and right after you can see a check if the requested URL is cscg.de. If not, we can just add a regular node by inserting it into the database. But if we have a cscg.de URL, we are starting a new screenshot task. This will be executed in parallel in a thread, so let's look at this thread. The screenshot task thread takes the new node ID. It was generated at the start of the function, and it was also used to create this placeholder node processing screenshot. So we are just passing the node ID as a reference to the placeholder node. And we also pass in the body, so the URL that we are requesting. Inside this thread, we are now calling the async function screenshot. This function now connects to the Chrome service. It is using Puppeteer for that. Unofficial Python port of Puppeteer, which is a JavaScript headless Chrome browser automation library. So this is just a Python library to automate and control Chrome. And it controls Chrome via the Chrome debug port 9222. And I think this code is pretty self-explanatory. We first create a new incognito browser window, then we create a new page. We navigate to that URL, we sleep for 10 seconds to wait for the page to be fully loaded, we extract the title, and we also create a screenshot. And then we close the browser window again. This image is then stored in the database by updating the node we created before as a placeholder. So far it looks pretty solid, right? Where is the vulnerability now? Maybe you already noticed a first issue. But first let's check out the third service, the admin service. And here we can also see the flag.txt file. So the admin has the flag. The Docker file starts similar to the Chrome service. It also installs Chrome, but then doesn't start a headless browser. It simply executes admin.py. The script opens the flag and then wants the IP of the main web app and creates a flagger password, a random value. The main code then starts in main, where we execute an endless loop. So here we also use Puppeteer. But this time we do not connect to a remote Chrome service, but just access the locally installed Chrome. We create a new browser and are now simulating a user. So this admin service is just simulating another user using the screenshotter app, a user who has the flag. So what does this user do? The user opens a new page and navigates to the screenshotter site. It then waits for 2 seconds and then enters the login credentials of the Flagger account using the random and secure Flagger password. So we probably cannot brute force that. After the login, it will then add the flag node. This admin user creates a node with the flag, and after that it also requests a screenshot from cscg.de. So now we know the goal. We need to get access to the nodes of the Flagger user. After waiting for a bit, sleeping for 10 seconds and reloading the page, it will eventually look up all nodes and then delete the nodes that were created. After that, the page is closed and the next user simulation loop starts. Cool. To summarize, this is a simulated user who owns the flag, which means we need to somehow attack this user. And given that this user is using an actual browser to perform actions, it is a big hint that the attack has to be a browser client-based attack. So we need something like a XSS or CSRF. By the way, if you are now inspired by this challenge to find the vulnerability yourself, now is your last chance to pause, because next I will tell you about all the puzzle pieces. 3, 2, 1. So we just learned from reading the code what the target user does, and that we need some kind of client-side attack to leak the nodes of Flagger. Those nodes contain the flag, so how can we do that? Well, an XSS is probably the most typical and most powerful way to leak information, so let's try to find the XSS. Feel free to try find it yourself, because I will just show you where it is. This web app is using Flask templates. I think it's using Jinja 2 templates under the hood, and generally they are secure. When you use curly braces to output user-controlled data, it is properly HTML encoded and safe. But there's one exception, and it is here. When you have a node that is an image, so a screenshot, then the alt text of the image is set to the title, but it's missing the quotes. And template engines like this are not context aware. The encoding doesn't know if this is just an HTML context or an attribute context. But the encoding is generally safe, just not in this particular context. Because if an attribute is missing the quotes, there are no special characters needed to get a XSS here. If the screenshot title contains a space, we can break out of the alt attribute and we can add additional attributes. For example, on load, which is executed once the image is loaded. Boom, XSS. Okay, so this is a XSS you can easily find by basic static code review if you have the experience about the typical pitfalls of template engines like this. If you didn't know that, now you know. The XSS is great, but once you think about it, how it could be used, you realize it seems useless. You need to be able to control the title of a website requested as screenshots. And the Flagger user is requesting cscg.de, so how would you influence the title of that page? It seems impossible to XSS the Flagger user this way. But who knows? This is just one puzzle piece that we can put into our pocket, and maybe it can become useful later. Let's see. Now, we cannot attack the Flagger user, but could we just, as a proof of concept, attack ourselves, a self-XSS? Well, if we could make a screenshot of arbitrary websites, then we could just create a website with a malicious title. And here is another puzzle piece you might have noticed earlier. The check for the allowed URLs is done with starts with. This means we can fully bypass the domain check. We could just use our own domain and use it as a subdomain. So for example, cscg.de.liveoverflow.com. This URL would be allowed. But there's one more trick. Actually, you don't need to use your own domain. You can also just use @ separates the URL into username part and the actual domain. So http cscg.de @liveoverflow.com would simply point to liveoverflow.com, and cscg.de would be a username that is just ignored. Let's try it. Submit the test URL and requesting screenshot. It seems to work. Let's give this a moment. And here we go. We got a screenshot from liveoverflow.com. Okay, with this bypass we can now test the XSS. To do that, I create a test HTML page with the XSS payload in the title. Then I start a local test server using Python, which will listen on port 8000. But locally accessible doesn't help us. The Chrome service needs to reach it. So then I'm using ngrok to get a public domain that is tunneled to my local test server. So by requesting cscg.de at the ngrok tunnel URL, I can make the Chrome service request my test index.html page. And of course, processing the screenshot takes a moment, but boom, here we go. We got a XSS. But unfortunately, we still don't know how we could XSS the Flagger user with that, because right now it's just a self-XSS. But let's see, more puzzle pieces, more is always better. So what else could we do with the domain bypass? Any ideas? Well, now we have a pretty much unrestricted SSRF, server-side request forgery, to request screenshots from arbitrary websites. Is there any other internal service we could try to make screenshots of? Maybe the Chrome service. Let's try it and see what happens. We just have to take the exposed Chrome IP and the port 9222. Let's submit and wait. As always, takes a moment. And here we go. We got a screenshot. Inspectable web contents. So this is maybe where a bit of research has to start. Probably many of you don't know the Chrome DevTools protocol, but you can find lots of resources about it online. Or you can also play with it yourself. To do that, you could change the Docker compose file to expose this port and then restart the whole service. Now you have direct access to it in the browser for testing. So here it is, port 9222, inspectable web contents. It takes a moment, but then shows about blank. And in the DevTools, we can see that it accesses an API endpoint, JSON list. Here it is. Title, about blank, and a WebSocket debug URL for it, as well as a DevTools frontend URL. And when you refresh it a few times, for example, when you request a screenshot or when Flagger requests a screenshot, another entry appears. Here is suddenly a page requesting cscg.de. So you can use the domain check bypass to request a screenshot of this JSON data, and it will leak some information about what pages the Chrome service currently has open. Let's do another test. We can wait for Flagger to request a screenshot of cscg.de, and once we see the message in the activity log, we can quickly submit our URL to the list of pages. We wait for the screenshot, and here it is. Here's the page where we request the list of pages, and here we have Flagger requesting the cscg.de page. But what exactly can we do with the WebSocket debug URL? This requires a bit of research, but if you, for example, Google that field name, you might find references to Puppeteer. And we learned earlier that Puppeteer is a library to automate and control Chrome. So could we maybe use this debugger URL to control Chrome like we also did in Python with Puppeteer? That is exactly what we're going to do. This protocol is used by, for example, the Chrome DevTools. So with this, you can do everything the Chrome DevTools can do, including, for example, redirecting the page to a different site. A site maybe with a XSS payload in the title. So here's a rough tech idea. We could request a screenshot from the Chrome debugger list to get the secret debug URL of the page Flagger is requesting. We can then probably use the debugger protocol to redirect the page away from cscg.de to a site with the XSS payload. When the screenshot is then done processing, the XSS payload will be placed into the list of nodes for Flagger. And when Flagger then looks at the nodes, it will be executed. And this XSS payload then just has to steal the private nodes. This sounds like a really good plan, except there's one issue. If Flagger requests a screenshot and then we request a screenshot of the debug list, then the Chrome service will load the list fine, but it will wait 10 seconds before it actually is taking the screenshot. So after 10 seconds, the service takes a screenshot of cscg.de, then it will take a screenshot of the page list. Now we have the secret debug URL, but also the service is done processing it, and the page doesn't exist anymore. So this is useless? We cannot do anything with that? Well, now you need a bit of creativity. Can you think of a way how you can still make this attack work? There's a small trick, and it actually took me a bit to come up with this myself. So pause if you want to think about this. Otherwise, I will share how my exploit works in 3, 2, 1. Okay, first we get the Chrome IP from the activity log, and then we wait until Flagger deleted a node. This is needed to get the right timing. This message means soon Flagger will request a screenshot. And here is the trick. We are timing our screenshot to be started before Flagger requests cscg.de. But we are not requesting the page list. We request this index.html site. And this site simply has a timeout. So it's waiting for 7 seconds and then redirects to the endpoint, leaking the debugger URLs. So we request our screenshot, the index.html is loaded, Flagger requests cscg.de. After 7 seconds, we redirect to the debugger port list, and after 10 seconds, the service takes a screenshot of it, and this will now contain the Flagger cscg.de debug URL. But thanks to our precise timing, the Chrome service still hasn't completed the screenshot for cscg.de yet. Now we need to be fast. Very quickly, we need to get the debug URL, and I'm using OCR for this, specifically Tesseract. This can extract text or the URL from the image. And once we get the secret debug URL, we can now launch our actual attack. We request another screenshot with our attack.html page, and this now creates a new WebSocket connecting to the debug URL and executes a page.navigate. So we force the browser to navigate to this XSS page. Now this page does not show CSCG anymore, which means after the 10 seconds are over for the Flagger screenshot request, the screenshot is created of the XSS HTML page. And we successfully got a XSS into the nodes of Flagger. This XSS payload is simple, it just takes the whole document body.txt, so the complete text of the website, and sends it with a GET request to a web server of mine, leaking the flag. That's it. This was the challenge screenshotter. Let me know what you think. I really like this challenge because it is based on an attack I found on a real web app. This is not guessing, it's not black box. You have the complete code available, so I think it's a great challenge to practice doing security audits. I hope you enjoyed this challenge, and congratulations to everybody who solved it.